Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone, today we have with us Marjorie Lad Parada, who is a researcher at Stockholm's University in Sweden. Hi Marjorie, how are you?
Hi, thank you. I'm doing well. Happy with spring. What about you?
Well, we were happy with spring in Germany until last week, and now we are back to winter. But hopefully, when you're taking over the account, we will have spring again. But yeah, looking forward to learning more about your research and about you and your scientific journey and everything. So let's start with your scientific career so far. So please tell us about your career.
So I think I have a slightly unorthodox background in terms of my scientific career. I'm not one that started her undergrad and then pursued a master's and then a PhD and then just followed the academic route from the beginning. I started by doing a bachelor's degree in food technology back in Mexico.
Food.
I really thought that my life was going to be, like working in industry, developing products. And I'm still like a big foodie. Don't get me started on food because I will never stop talking about it. I just find it absolutely fascinating. And I did work in industry in an applications and R&D department for several years. But then I realized that as much as I liked it, I needed more of a challenge. I wanted to have more, how to say it? Basically, yes, like not just challenges in applications, but trying to understand why things happen. Because this is one of the things that I noticed that I was lacking, understanding of how and when things happened. And that was also limiting in part of my work. So I decided, okay, no, industry is great, but I want something more. I want to understand more fundamentals, more theories. So I decided then to do a master's, still thinking maybe I'll end up in industry still. I mean, this will just be like another step towards maybe a different direction. So I did a master's in the UK, Leeds University. And once I started doing my master's, all of a sudden the world of academia came knocking and said, look, we're really cool actually, and I'm gonna like it. So I was like, maybe.
You are cool.
This does sound really cool actually. And so I looked for PhD opportunities within England. I was actually accepted in two different things. So one that was a doctoral training program, and then finally the PhD position that I accepted that was also in Leeds and had to do with cocoa butter. So the fat in chocolate and its crystallization and how it was impacted by different processing techniques. Yeah, so temperature and pressure.
Wow.
So this was in collaboration still with industry. So you see, like I was still not living it. It was like, I know, I still like it. Food is so cool and nice. I love
Still kept holding on to it somehow.
I guess we like giving something that seems normal to us, right? And with this, I actually started my route into the world of X-rays, which I had never used before. I mean, my only reference about X-rays in structural studies was about the DNA and
DNA.
DNA, exactly, because with Rosalind Franklin taking the actual slide of DNA of the X-ray scattering, and then in combination with the work of Watson and Crick, this is how they actually found the structure of DNA, this helix. So actually X-rays are very important, like have been key in understanding the structure of life, for example. So I found it fascinating, but of course I did not study physics or like basic chemistry. Like my studies were applied science, basically. So it was quite of a challenge. But then I was like, okay, X-ray sounds so amazing. and I do want to stay in academia. Like, I left on the side industry, at least for now. And so I looked for a postdoc, and I was like, oh, what can I find? Like, what suits my interests and my capabilities? And I saw this postdoc opportunity here in Sweden that they said, oh, if you want to work with amorphous ices under super cool conditions that have been obtained by pressurizing ice and understanding water in super cool conditions and using X-rays and traveling. And I was like, oh, this sounds amazing. This is what I want. But you can see from the description, they basically said, we want a physics student for this. And I was like, oh no, should I not? Most of the people I knew were just telling me, well, you can apply, but you probably won't get it because, I mean, they want a physics student. I was like, this is so sad. Until I got the best advice. And they were just like, you know what? I know it sounds like you're not the profile, you don't have the profile they're looking for, but you're interested and you know why. So what I recommend you to do is write to the PIs, so the investigator, and tell them who you are, why you're interested, why you think you might be good for the position, and ask them if it's worth applying so that you don't waste their time and your time in filling in this very long application form and writing stuff.
Right.
And so I did. And they replied immediately, and they were just like, okay, please already give us your referees and fill in the application form. But already when they asked for the referees, I knew that there was some interest from their part.
Absolutely.
Yes, I was super excited. So I applied. And actually, on the date that the application closed, I immediately got an email of, when can you come for an interview? I was just like dying. I was like, no, this can't be happening. I was like, okay, I still probably won't get it. I'm not a fit.
No.
Like, I should still go. I mean, they're going to pay like for me to go to Stockholm. I mean, which is prices. I'm not going to complain. I'm going to go.
Absolutely, yeah.
So they asked me to come here at 9, and I arrived, and then it was just a full day of like talking to different people from the group. I even had lunch with them. They invited me for dinner so that they could know me in a more social context to see if I really fit with the team. But actually, before the dinner, like after lunch, they had the meeting, and after the meeting, the PI went into the room and he said, well, we want you.
That's amazing.
Yes, I literally was completely shocked, and I could not say anything. I just stared at him blankly like an idiot for like a few minutes, and he was worried, like, is it okay? I know it's surprising, but I mean, if you don't want to, you don't have to, but I would really like you to work for. And I was like, no, I just can't believe it. It's just like, this is like my dream position, and I'm getting it. This is amazing.
Right.
Yes, and then they invited me the next week after that to join them to a trip to Korea to this X-ray facility so that I could start getting involved with the project. I mean, of course, I knew that I had to ask my supervisor if it was okay for me to just up and leave for 2 weeks. And yeah, so the following week, I traveled with the team to Korea, completely jet lagged, not knowing these people, spending over 12 hours a day with them. And then I went back to Leeds, and 2 days later, I graduated. Oh no, 2 days later, I went to a conference in Sweden, and then I went back, graduated, and went back to Mexico for Christmas holidays. And that's how I got here.
That's quite an exciting journey you've had. Very, very unique, from food technology to how you ended up in your current position. That is so cool. So how long have you been doing this water research in Sweden at the moment, like as of
2
now?
2 years now.
2 years now. Wow. So it's still quite fresh.
Exactly.
That's awesome. That's really cool. So your current research, you did speak about it quite a bit in the short podcast, but what I want to understand from you is that, first of all, it's so cool. Every time I say cool, there is the bad pun that is like, but your current research that you're doing right now, where does it fit in this big picture of materials or nanoscience?
Okay, so in terms of nanoscience, thinking that we're looking at the nanostructures, Literally, that's the only thing that I look at, the nanostructures within water, either as liquid water or in terms of what we know as amorphous ices. Now, you might be wondering by now what these amorphous ices are, because I've talked about supercool water is the water that's liquid and it's at temperatures below 0 degrees.
Right.
But amorphous ices are actually the most, I would say, the ice that you will find most often in the universe, not in planet Earth, but in the universe. And does it look differently from the normal ice that you just add to your lemonade when you have lovely summer's days? Yes, dreaming of summer here.
Yes.
Clear ice that you add to your water, it's crystalline. So basically, it has a very periodic structure. So you repeat the structure over and over, like layers and layers and layers of a parfait, if you think of it. Layers of onions. It's always the same structure over and over again over long distances. Whereas amorphous is more like your windows glasses. So basically, it's something that is solid, but it does not have this repeatable structure over long range order. So again, this has to do with the nanoscience.
Right. Okay.
So these amorphous ices, you find them at ultra low temperatures. So again, way, way, way far away from the 0 degrees. I mean, even to liquid nitrogen temperatures, so 77 Kelvin. And also you produce them by applying pressure. So we actually have these very tiny samples that are like maybe 1 millimeter wide, thin layers. And then we have a machine that's taller than me to press them with gigapascals. Is like the most ridiculous thing. But that way you can apply enough pressure in a very small area.
Right.
And what it does is just destroys the structure, the periodic structure of your ice.
So did I understand this correctly? So there is the layer structured, and then you crush it, so to say, crush the ice. You crush it, and then it becomes amorphous ice. Is that?
Yes. I mean, some people might have actually questioned whether it's just really amorphous or if it's just crystallized that are just too small for us to see. However, besides, I mean, this is only the first phase. Afterwards, you decrease slightly the pressure and also you increase slightly the temperature. So instead of 77 Kelvin, so
Right.
you go to 160 or 140 Kelvin, which are still way, way below 0 degrees. And with this, the molecules relax. I mean, first you stress them, the poor things, by pressuring them, and then you let them relax a bit. I mean, they're still under pressure, but not so much, so they can take it easy, and they can find new rearrangements.
And then you watch them while they are relaxing.
Actually, at the moment, we have not been able to follow this with the X-rays because it's really hard to have the combination of high pressure, like very well-defined pressure, and the low temperature and the controlled low temperature. So what we can do is that in these different stages of like pressures and temperatures, we extract them. So once we reach, okay, like we pressed it and increase the temperature, then you cool it back down quickly to the 77 to the liquid nitrogen temperature. And that literally freezes the molecules wherever they are. So you can then keep your samples on the liquid nitrogen. You can ship them to Korea, to Germany, to the States, wherever you want, as long as you stay with liquid nitrogen.
Right.
And then you can fire the X-rays, and then you can control the temperature by increasing it slowly.
Okay.
So this is how we measure them. So basically, we have to prepare the sample, freeze it even more, so that the molecules don't move, and then we can study them.
Okay. This is so fascinating for me. It's a complete new world of nanoscience has opened for me. This is so cool. And it does sound like you do have a lot of interesting research projects that you are involved with and you were all involved with so far as well. And now this is a tough question, okay? I realize that while I'm asking this question to you. But if you have to pick one research project that you're most proud of or the most quirky or fun one, I know it's tough, but could you pick one and explain it to us in simple words in the section we call In Other Words?
Okay, so I know that I have been speaking about this ice, but one thing that I was very proud of was actually during my PhD with cocoa butter. Yes.
Tell
So
us more. Cacao butter. Please tell us. Yes. Food and please go on.
I mean, cocoa butter, yes, it has been studied by X-rays for a very long time, more than you would think, actually.
Why? Sorry.
But there are new techniques. I mean, but then you just know, okay, the structure looks like A, like B, like C, and that's all that you really know. Um, but see, I was actually interested in also what happened when you heated it. So you melted it and then you cooled it down to crystallize, because sometimes it crystallizes in a different way depending on the temperature at which you're melting it, for example. And it's really hard to pinpoint when it starts crystallizing because, of course, you have very, very tiny structures in a big bunch of melted cocoa butter. So it's hard to see. Um, so I try to use this technique that's called nuclear magnetic resonance. So here you focus on the hydrogens. And what you can measure with this particular technique is sometimes how the molecules diffuse, how they're moving in this melted condition. And in particular, there is a newer technique within NMR, for short, that's called fast field cycling. And this is because you study how molecules move under different frequencies. So you can
What is
see
it called again? Sorry.
fast field cycling. So you cycle, you change the field, the magnetic field that you're applying to your product, basically. Because by
Okay.
changing the frequency, you can see motions, like movements of the molecules that happen at these different frequencies. So that is at different time scales.
Uh-huh. Okay.
So this technique had never been applied to cocoa butter, actually, like not even in fats at all. There were very few studies in liquid solutions. So it just happened that it was available in Leeds, and I had just contacted the researcher that owned it. So I was like, why don't we do this? And he was like, yeah, I mean, if you want to and you have time, well, just go for it. Um, and again, it was something that I really had to understand how it worked
Okay.
on my own, because I had no idea about this nuclear magnetic resonance. I mean, the closest to magnetic resonance is the things that they do, in medicine to see at your knees, at your brain, and so on. But I was like, okay, but what about this thing? So I had to learn by myself a lot of the background behind this technique. So that was actually quite hard. As I said, I do not come from physics background, so I really needed to go back to the books and like finding YouTube videos about how it works. And then I was so surprised because I really got interesting results. We noticed that this technique was very sensitive to when crystallization started. You could see how the motions changed as the temperature changed. How the molecules got faster and a little bit slower and even more slow as they started to crystallize. And it was the one where I got my first two papers published of my PhD. I thought it would be X-rays because I was using X-rays heavily. I was like, this is where I'm going. And then all of a sudden, it was this technique that I used as a side thing and that had never been reported in fats. So yes.
Wow. 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 That's really cool. That really sounds super cool. And I can understand why you picked this as one of the projects. Let's put it this way, that you're most proud of. I'm sure you're proud of all most of your projects. So, but yeah, no, this sounds really cool. Awesome. So, Marjorie, what I also want to understand from you, I mean, you clearly love the research part of being a scientist, but what else do you like about being a scientist?
One of the things I like about being a scientist is that you really don't have like a structure time. I mean, this can be hard because then I guess it could be very easy to just laze around. But it's not like I'm expected you have to be here at 8 and then you have to leave at this time. Like, no. We need research. This is the objective. We need to get it done. And then you time manage, basically. So
Right.
I mean, of course, there are times when you just have to keep going no matter what happens. But others, you know that, okay, instead of like working 9 to 5, the day is beautiful. I'm just going to take a long walk and then I'm going to come back and maybe I stay for an hour longer, but that's fine.
Right, flexible hours, yeah.
Yes, very flexible hours depending on what you're doing. I find it that it's a challenge, of course, because you have to understand things, how to make things work. So it really develops your creativity, which is something I think not many people outside of science realize that actually science is one of the most creative um,
Fields.
things you can do for a living. You
Right.
always have to solve problems and think outside the box to understand or know which experiment you're going to do. So this is something that really pushes your creativity. And actually another part, and I know that not all scientists wouldn't necessarily get involved with it, is the science communication part. I think it's incredibly important that we not only tell about our science to fellow scientists, but also to the world. And this part is amazing. I mean, building this connection with people that are not from an academic background or to potential budding scientists, that's always good. It's really amazing. So I've had the opportunity of being involved with some talks, popular science talks, and it's really nice because then sometimes you get questions that you would have never thought as a science, like because you're so focused in your work that you do not see around it.
Right.
So
Right.
this part I really really enjoy as well.
Right. Right. Okay. All right. Yeah. These everything that you mentioned, it makes complete sense. I mean, totally. I can understand. I can relate to that. Flexible hours, being able to solve uh, not challenges, but yeah, kind of challenges or mysteries, so to say, in the most creative way possible, and also science communication. That's definitely interesting. And again, I'm glad we have scientists like you who are active researchers who also enjoy science communication and are involved with science communication. That's always good. Um, what I also want to understand from you, Marjorie, is um, what advice would you give? Now, there are two ways you can answer it. The first could be that go back in time, and what advice would you give yourself if you were starting out your science journey? Or the second option is, of course, what advice would you give to the scientists who are starting out now, like the budding scientists that you mentioned?
Well, as for myself, sometimes I think that I want to tell myself that maybe I should study some pure science or at least chemical physics, to help me with my work. But then again, I did enjoy my time in industry and I love understanding food processing and the chemical changes that happen in food. So I do not regret it. But yeah, maybe I would say like study on the side a little bit more on these things. Um, but yeah, I mean, this is now because I know what I'm doing at the moment. However, what I think has driven me and has led me to where I am now is the fact that, yes, despite of this, my not having the perfect background, you could say, or the expected background, was that fact that I actually dared to do it. So it's super scary, I think, to do something that's outside your area of expertise,
Absolutely.
really good at. So, like that bit, I would tell to budding scientists, like, don't be afraid to try something that is outside the area where you have shined before, because you might find something super exciting and where you can develop and grow. So yes, don't limit yourself, basically. Uh, Even when people tell you like, no, you won't get it, if you really want it, go for it. I mean, as they say, you already have a no as an answer if you don't try. Whereas if you try, there is a possibility.
Absolutely.
And also be open to possibilities, because sometimes you think that what's going to be your life or like your life objective or whatever you're going, like, this is my passion, this is my dream, I will follow it, and then the dream turns out that it's completely different from what you had envisioned, because of course you cannot know how it is until you're in it.
Yeah.
So if that's the case, that, oh my gosh, my dream is not what I thought it would be, well, I mean, you tried it, you achieved it, that's already amazing, but now you know that that's not where you want to go, then change. Change is
Absolutely.
actually the best thing and the only constant thing in life, so don't be afraid to change your direction. It does not reflect bad on you as a person, but rather actually just means that you know yourself enough
Yeah.
for something else.
Right. Yeah, that makes sense. That's some really sound advices there. Thank you very much for that. And I, I mean, you do have a lot of experience being a researcher, being an active researcher, and I hope your experience, research experience, has been wonderful so far and will continue to be wonderful in the future as well. However, if you had three wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
I guess one of the things that is key, and somehow feel that it comes too late in our formation as scientists, is the writing part.
Oh, yeah.
I mean, the two key things of a scientist that I don't think many people see is that you need to be incredibly creative.
Yeah.
The other one is that you have to be a proficient writer. Why? Because all you do, I mean,
It's right.
besides research, all you do is actually write. You have to write papers, you have to write proposals, you have to write letters of support. You're always writing because this is the way that you can express your science, you can communicate it the easiest way, and also it's a way that you can tell people why it's important. So this is the main thing that I think would be great to have more support and more ideas like, okay, what is expected, what makes a good paper, what makes a good proposal. So I think this is the part where I would need more. Yeah, I would. So yeah, I would appreciate some support, like further support. So that's the thing. The another thing that I could ask for better support, I guess, especially with this internationalization, I mean, we're all working usually in an international group, and then you move to a different country. I mean, some people move like a lot, others less, depending on your situation and preferences. Um, but this actually makes it harder sometimes to be aware of what are, like, for example, the people that can give you, that can finance your science. You don't necessarily know all of the research councils in every country and all the minor grants that you can ask for. So I think if universities really supported their researchers, their incoming researchers, by telling them, oh, these are all the things that you can apply for, or like this is where you can look for them. This is what you need. This is how we support or not support you. This is, and so on. So I think that's a big thing.
Right. That's the second thing. Third thing now. Third wish.
The third thing, I'm just gonna be silly, admittedly,
Go ahead.
because I have a love for cats and dogs. And I miss having the possibility of having these pet therapy dogs that you could just cuddle whenever times were too stressful. And I think that would be absolutely amazing if that would be like a constant thing around universities. You have their pet therapy session scheduled once a week or once a month. You come here, same time, same place. That would be amazing.
That sounds, especially the third wish. I hope it comes true. I hope it comes true tomorrow, Marjorie. I really hope so. Not just for you, but for everyone. Whoever needs it, wants it, doesn't know it, they need it. Everyone needs it. Any kind of pet therapy. Absolutely. Cats, dogs, snakes, spiders, whatever you want. Yes, absolutely. But no, also the first two points the first two wishes that you mentioned with the writing, and this traveling scientists and knowing where to get the grants and like the funding agencies and all of that. I think that's also very, very important, and often not talked about. It's just assumed that you know how to write. It's just assumed that you know where to ask for money, or where to go when you are stressed. It's just, so thank you for highlighting that. I hope it does come true. All three wishes do come
Thank
true
you.
for you. This has been wonderful, Marjorie. But before I let you go, I have one last question for you. We are in 2020 now, and we all lived through the very, very difficult year that was 2020. There were pros and cons to the year. Would you like to share some of your learnings from the year 2020?
I guess it would be, do not take anything for granted, or anyone for that matter. I think it highlighted how important it is to really give priority to the things that matter to you the most. Be that job, be that your family, be that your cat. Doesn't really matter what it is. Because as much as it's said, I mean, all we have is now. So if you don't do it now, if you don't prioritize it now, you don't know if you'll be able to in the future.